Hi. This week we're going to learn more about modeling differential equation, and in particular we will solve a very specific differential equation known as the population growth and the logistic equation. So let's first look at chapter 7.5. This works the very basic modeling question. So let me solve this activity, and I think everything should be clear from there. Okay, so let's solve this activity. So first of all, you have to set up the equation, right? So as you can see, the question says that the bank account grows by 5% every year. A is the amount of money in the account in the year T. So first question is, what is the rate of change of A with respect to T? And that's very natural, right? This is just dA dt, right? And remember, this is a function of T. Okay. So meaning, say if at is the function t square, then dA dt is the function 2t in that way. Okay, perfect. So dA dt is the function that depicts the rate of change of money with respect to t. So now you are withdrawing $10,000 per year, right? So the question is, what is the rate of change? What is the total rate of change, right? So see, dA dt, this is the rate of change, right? And what is that? This is your present money in the account minus $10,000, right? Okay, this shouldn't be 80, my bad. This should be 80 over 20. Why is that? This is because this is the incoming money through interest. And this is outgoing money, right? That is because you are transferring it. Make sense? So remember, the interest rate is 5%. 5% means it's 1/20th of your existing bank account balance, right? Okay. Now they are asking you to sketch the slope field. I will leave that to you as the exercise because these are something we have covered in the last classes. Um, okay. Second, the third, fourth part is that you initially deposit $100,000 in the account, right? So how long does it take for you to deplete the account, right? So see, that differential equation is as before. However, now there is an initial condition saying that A0 is 100,000, right? So the question is, when, that is, for what t, at is 0, right? So naturally, you have to solve this differential equation, right? So solve it. So dA dt is 1 over 20 a of t minus 10,000. So how do you solve it? Well, perform the separation of variable. So dA dt equals to at minus 200,000 over 20. Bring all the a together and all the t's together, and then do the indefinite integration, right? So this is going to be log mod equals to t over 20 plus c, meaning a equals to c1. Okay, let me be more precise. A minus 200,000 equals to e power c plus t over 20, which you can write as e power c, e power t over 20. Remember that this c is the integration constant. So this is an arbitrary real number. So I will call e power c as a new constant c1. So this is c1 e power plus 200,000. So this is a, or a of t, right? Now plug in t equals to 0 to use your initial condition. That means c1 plus 200,000. But a0 is 100,000, right? So that means 100,000 equals to c1 plus 200,000, meaning c1 is negative 100,000. That means a of t is negative 100,000 e power t over 200 plus 200,000. Okay, now you want this left hand side to be 0. So say at t equals to t0, a of t0 is 0. So plug in t0 in this equation, right? That means 0 equals to negative e power t0 over 200 plus 200,000. That means e power t0 over 200 equals to 200,000, meaning e power t0 over 200 is 2, meaning t0 over 200 is log 2, meaning t is 200 times log 2, right? So at this time, so in 200 times log 2 year, a of t will become 0. That's it. Okay. And number f, I'm not going to do it entirely. But now your initial deposit is 300,000, right? Okay, no. Okay, E and F. Okay, so what is the smallest amount of money you need to have in the account to guarantee that you never deplete your money in the account? Okay, so now the question is different. So they're saying find A0 such that the solution to the initial value problem DADT. I mean this above initial value problem that we just saw with initial value equals to A0 will never become 0, right? So the question is as follows. So look at the previous problem. We saw that if my initial value is 100,000, then in eventually in some year, this money will ultimately become 0 as long as you keep withdrawing $100,000 from the bank every year. Now, the question is this. Instead of the initial deposit to be 100,000, what is that amount of money that you should deposit in your bank in the first place so that this money will never vanish, meaning this A of t will never become 0, right? So again, we remember we solved the solution to differential equation does not change, right? I mean, this solution will not, sorry, I mean, this solution will not change, right? So let us copy this. Recall that the solution to the differential equation without the initial value was this. So since I have not invoked any initial value computation, I don't yet know what this constant c is. But there is some constant c. If you assume some initial value, then this constant will be evaluated. For example, here the initial value was assumed to be 100,000. Hence, this value of C1 become to be negative 100,000, right? So I don't know the initial value yet, but it will be something. So let us find this out. So here our initial value is A0, right? So let's plug that in. So A0 is C1 plus 200,000, meaning C1 is A0, this number A0 minus 200,000. So our differential equation has the following solution. Right? Now you are inquiring whether this expression can be 0 for any value of t. Let's see. Say a of t0 is 0. meaning meaning A0 minus 200,000 e power t over 20 equals to negative 200,000. Right? Okay. Now inspect this expression very carefully. If A0 is less than 200,000, what happens then? Then then the left hand side of the equation is negative, right? Meaning e power t over 20 is negative 200,000 over a minus 200,000. But this expression, sorry, this expression is negative, right? Meaning this guy is positive, right? See, I mean, I assume that 200,000 is more than a0. So this is a positive exponent and this is a positive component, this is also a positive component, right? So there is no harm for me to take log now. So t over 20 is log of 200,000 minus a0, meaning, sorry, this should be t0. T0 is 20 times this guy, right? So that means, so if A0 is less than 200,000, there exists a real number such that A of T0 is 0, right? We just proved it, right? So assuming this condition, we just found out the value of t0 for which this equation holds, meaning that this equation is a of t0 is 0, right? However, see, now if a0 is more than 200,000, then this left hand side is positive, but the right hand side is negative. So this equation can never hold. However, if a0 is, then LHS is non-negative. LHS of this equation. LHS of star. And you can see the right hand side is strictly negative. Meaning, so that means star can never be true. So A of T0 can never be 0 no matter what T0 is. Meaning A of T0 will never be 0. So as long as your initial deposit in the bank is $200,000, your bank will never be 0. Your bank balance will never be 0. So that's the point. So that answers question F. Your initial deposit is 300,000. So, oh yeah. So now okay, I leave number F for you. This is kind of a brain teaser. So I expect you to do it. So the question is, the differential equation is this, and the initial condition is this, right? What value of C0 will guarantee that A of t is never 0? This is a very fun problem. I mean, see, there are two ways your bank can be finished. Either your initial deposit was too low, which we saw in the last problem, right? We saw that if the initial deposit is less than 200,000, it will ultimately become 0 as long as you keep um, withdrawing $100,000, $10,000 every year. Okay, so let me rephrase. Like, there are two ways your bank balance can be 0. One, you are depositing too much money every year. Sorry, you are um, withdrawing too much money every year, or your deposit is like smaller. For example, we just saw that if you keep withdrawing $10,000 every year, then any initial deposit of less than 200,000 will guarantee that your bank will ultimately be 0. Your bank balance will ultimately be 0. But if your initial deposit is more than $200,000, then if you keep withdrawing 10,000 every year, you are still okay. Sounds good? And now the question is this. Suppose that my initial deposit is fixed, with $300,000. How much should I withdraw every year so that my bank balance never becomes 0? So last time it was $10,000 every year. Now my initial deposit is higher. So naturally you should guess that your annual withdrawal can be slightly higher than $10,000. But that's your question, like what this C0 should be, so that you actually can guarantee that 80 is never 0. So I leave that to you. Okay, I will give you more problems from this section for exercise. I mean, I don't actually have much to teach. So let's go to 7.6. So here we will learn about the so-called logistic differential equation. So what does the differential equation look like? Actually, let me get the screenshot from the textbook. So a logistic differential equation looks like this with some initial condition. Okay. And usually, not usually, all the time, the solution of this logistic differential equation will look like this. Okay. So how do you solve this? Essentially, you solve this using separation of variable and then something called the partial fraction decomposition. So um, instead of, yeah, I think we do not need this partial fraction decomposition right now. I will see, like before midterm, if I think that this is a good thing to cover, I will do it. Otherwise, you don't really need this method of solving logistic equation for this chapter. So let me try to solve activity 7.6.3 and try to actually solve a problem to show you how this kind of problem works. So this is perhaps one of the nicest example when you frame a question and you have a very explicit solution to the question. So, so here's a logistic equation. So, okay, first question is at what value of P the rate of, at what value of P the rate of change is the greatest? Now remember, rate of change is always this guy. I mean, this guy, right? And here is the graph of the function dp/dt with respect to P, right? So as you can see, the function dp/dt was increasing until n over 2 and then started decreasing from there, right? So that means the value of dp/dt at n over 2 is the highest. It's child's game, right? So answer of A is naturally. So this is a moment of lesson for all of you. So for differential equations such as this logistic equation, the rate of change, that is dp/dt, is highest when p is n equals to 2. So when the population reaches half of uh, the the n, then it is actually the dp/dt is actually the highest changing rate over there. Okay, so why do we say it p? Because it kind of models population. So suppose there is a enclosed water body such as a pond, and there are a bunch of fish in there, right? And you want to model by a differential equation their population. The differential equation would look something like this logistic equation. So that's why p always denotes the population. Okay. Okay. Now let's do number B. Now they're giving a very particular differential logistic equation, which is supposed to be Earth's population. And again, they're asking like at what value of P the rate of change is greatest, right? So we just saw in this last question that when P is n over 2, dp/dt is highest. And n is this guy, right? Right? So here k is 1 and oh my bad. Yeah, I have to rewrite this equation. So I have to bring it in the usual form. So dp dt is 1 over 0.002 p 0.025 0.002 minus p, right? So now everything is okay. So this guy, this is k, and this guy is n, right? So you want, so this is 0.025 over 0.002. Okay, you can actually simplify it a lot. So this is like 25 over 2 times half. So this is 25 over 4. So for p equals to 25 over 4, dpdt is highest. Okay. Now recall that the solution, as you can see in the question, is this 12.5 over something 1.0546 e power negative 0.025 t plus 1. So the question is, what is the population when t equals to 200,000? Okay, by the way, remember that what was our initial time? Um, I think I should be more precise here. So, mhm, yeah. So if you go to activity 7.6.3, so recall that our initial time t0 was 2000, right? Meaning when recall, and this is from, just to make a note, this is from activity 7.6.2. So when t equals to 2100, how much time has passed then? So when it is 2100 years, t is 2100 minus t0, so this is 100, right? So you should plug in population is p of 100, right? So population in 2100 is p of t, which is p of 100. Now plug this 100 in here and you will find the rest. Okay. Now again, according to the model, when will the population reach 9 billion? So this is number D. So you want PT equals to 9 billion, right? So PT is 10 times 9, 10 power 9. So solve T, right? Um, okay, this is very painful and I'm not going to do it. So it's left as exercise. Now, number 9. The last one is that, yeah, this is a very nice problem. So PT is n, as you can see from the general solution, P0 e power negative k n t plus 1. So what is P0? P0 is, as you can see, it is n minus P0, P0 times 1 plus 1, and this is nothing but n over n minus P0 plus P0 over P0, and this is nothing but P0. So this solution indeed gives you P of 0 as 0. So my point is that in this question, the initial time is this, right? So meaning P of 0 is, oh yeah, I'm actually, yeah, so T0 is 2000. Yeah, my bad. So, meaning that P of 0 is P0. And what happens when limit t goes to infinity? What does this expression mean? This expression is trying to capture what happens to the population when time goes by, or does this population reach any end? So see, as t goes to infinity, this guy, so as t goes to infinity, e power negative k n t goes to 0, right? Because k n all are positive number, right? Meaning p of t will converge to n over 1, right? Which is 1, n. So with time, this population will actually converge to n. So indeed, like this population has upper bound. It cannot like grow as long as it want. Okay, that's all about logistic equation. What you have to do is like you have to solve a lot of problem here, and I will give you a lot of problem. Okay, that's all. Thank you.